Smart Streams, a framework for storing big and fast data. Just want to give a disclaimer before I start off. This is not a product presentation. There's no product called Smart Stream. The purpose of this talk is just to discuss an architectural approach to solve a particular kind of business problem that we see quite commonly in the machine learning and the data engineering space. So hello everyone, my name is Vedant Jain, and I'm a solutions architect at Databricks. And today I'll give you a brief overview of the components of this architecture, and I'll break it down into a few components: machine learning, model storing, microservices, and then I'll consolidate these concepts in the context of Apache Spark and the streaming component within Apache Spark called structured streaming. And then I'll end with a demo. So quick raise of hands. How many people in the room have already heard of Apache Spark before? Okay, so quite a large audience. How many have actually worked hands-on with Spark? Okay, good. Okay, so to start out with machine learning, of course there are a ton of definitions, and a lot of us have our own definition for machine learning, but this is my favorite one. It's the machine can learn from experiences, and then, broadly speaking, there are two ways in which you can train a machine to do something. One is unsupervised learning. So if you have a ton of data already and you just want to find patterns in the data, unsupervised learning can help you with that. So for example, if you're a bank and you're trying to identify how people use their credit cards, and you want to bucket them in certain categories, but you don't necessarily know what those categories are. And today, this technique is also used by, say, online retailers to build recommendation engines, hospitals to build their patients, etc. And then there's a supervised learning technique. So, for example, if you have a human carries a smartphone, the smartphone produces axial data, and then the human engages in a number of physical activities. And so the human also trains the machine to understand or label what activity is engaging in explicitly. And then once he's done that, the model starts to classify or label the axial data without human intervention. That is an example of supervised learning. And in short, you use a training data set made by a human to teach the machine specifically what it needs to do. And this can also be applied across industries. So for example, it's commonly used in fraud detection in banking transactions, or even as simple as Alexa learning little nuances in your voice and improving over time. And there are other techniques such as semi-supervised learning, reinforcement learning, and transfer learning that also come under machine learning, but I will not talk about those today. And regardless of what machine learning technique you use, a data scientist will generally go through these steps in order to train a machine to do something, and the output of this process will be a model. And in any real-world scenario, you would want to make sure that the model either improves over time or it maintains its accuracy over time. And then once you have this model, you would want to, you will deploy this and you will use that to store any future data that you feed that model with. And this concept is known as model storing. Model storing has been quite commonplace. It's defined as a process of generating values based on a trained machine learning model, and it's already being used and historically being used in various industries. So, for example, some of the common ones are propensity scoring, that is a likelihood of the user to commit a certain action, affinity scoring, that is how similar are two products or users, attrition, that is the likelihood of a customer to drop your service and start a competitor service, credit scoring that you know already, and then anomaly detection, that is identifying a rare or invalid transaction. But when we talk about model storing on big data, we are faced with a number of challenges. It's not the same as the traditional way of doing model sorting if you were using software such as SPSS or SAS or something like that. And those challenges can be challenge of scalability. So a data scientist should be empowered with big data tools to build models on a very large amount of data. Also, since we are now in the era of fast-paced, fast-moving data being generated in many different formats from a number of different devices, you should have a highly scalable real-time engine that is not only ingesting this data but also generating scores or predictions in real time. And finally, the system should be dynamic. That is, it should be able to gracefully respond to changing requests and have an effective failover mechanism and ability to isolate errors and processes, etc. So the demo that I'm going to show you today, on a broad scale, I used PySpark, scikit-learn, and Docker. And I will in the end walk through some database notebooks as well. So I started out with a data set in a CSV format. It was data with, it was axial data in CSV format taken from various smart devices. And then I ran some distributed transformations using Spark. I dropped the null values, I calculated the moving average on a 10-minute window, and I converted that all these CSV files into a single Parquet file. So I ran these ETL transformations using Spark, and I was able to harness the big data processing capability of Spark to really pull the data into a much smaller data set, which could then be fed into a single node type process using scikit-learn. And then I used a random forest classifier to classify the activity specifically that the human was engaging in. And then again, went back to using Spark, did some cross-tabulation, and then finally I used k-means clustering. And the output of this process was basically 2 machine learning pipelines that I deployed in 2 separate Docker images and served using Python class. Now this is quite broken down. Databricks is actually coming up with, it's going to release a tool called NumFOCUS, which will allow you to build these machine learning pipelines, build hundreds or thousands of models, do hyperparameter tuning, and deploy these models in the cloud as well. And there's a talk about that Jules from Databricks will be giving tomorrow, so if you're interested, you can go to that talk tomorrow. So this brings us to our next topic, that is microservices. So essentially, software that is built with microservices is broken down into multiple component services. So each of these services can be deployed independently. And they normally run in containers, and they're isolated from one another. So the result of this, what we call a loosely coupled architecture as opposed to a tightly coupled architecture, you get many benefits out of this. But on a high level, you have a much more improved continuous integration and continuous development pipeline. The code is generally organized into business capabilities. So ideas of individuals or individual teams can be implemented without having to coordinate with a wider IT delivery function in the organization. And since the components are spread across multiple servers, and they can be spread across multiple data centers as well, it really complements your cloud activities. So a simple example is like with many large enterprises that we work with, they may have their data in the cloud, and they may want to use the scalability or take advantage of the scalability of the cloud, but they want to keep their intellectual property on-prem, on their on-prem data center. So a microservices architecture really allows them to do that. And finally, there's a concept of scalability and reusability. Since the code is modularized, you can take bits and pieces of the code and you can reuse them. And also it makes third-party integration with third-party services much easier. So the example that I'll walk you through today is a typical IoT use case. Let's say you have a company A that tracks user activity through smart devices, and it wants to provide tailored content to the users based on their behavior. So the general architecture is going to look like this. You have physical activity of a human that gets tracked by a smartphone. It gets translated into axial data. And then I have a model that I talked about that I developed earlier. It's a classification model that basically will classify this axial data into activities. And this is what I call perishable insights. So these are, you can't really do anything meaningful with this data, so it's perishable. So this needs to be fed into another model that was the clustering model, or the unsupervised learning model, which clusters similar users together and generates these affinity scores. And these are, this is what I call actionable intelligence, because you can actually take meaningful, you can derive meaningful information out of this. That is, you can now take this information, you can bucket similar users together, you can target them with certain kind of ads or targeted content based on their activity. So essentially in this architecture, you have 3 microservices. They're of course deployed independently from one another, so they're continuously enriching data as it comes in from one service to the other. And there's isolation, there's complete isolations in case one service goes down. You can fix it, you can redeploy it, or if you want to update your machine learning models and you don't want to affect the general flow of data, you can take the service down, update it, and then bring it back up. And that's the advantage of this modularized, isolated architecture. And then, you get because they're independent of one another, you also get scalability. So if you have to scale for, let's say, the classification process, you can scale your microservices just for that purpose, but not necessarily for, let's say, your web services, right? They're completely independent of one another. And finally, you need a way to allow free flow of the data between these services, for which you need a consistent, a scalable, fault-tolerant event processing system. And you get that from Apache Spark. Okay. So now I'm going to talk about Apache Spark, and more importantly, the streaming component of Spark. So before that, I'll give you a brief overview of what it is for the folks in the room that have not worked with Spark before. So Spark is a general purpose compute engine for doing distributed processing. And it has a wide variety of applications, such as ETL, being able to do ETL, interactive querying, and even advanced analytics, such as graph processing, machine learning, and streaming, data analysis, all from one engine and all from this one general programming paradigm. For loading and storing data, Spark integrates with many storage systems, and really it forms the core of a very extensible open source ecosystem. And then in terms of API, Spark also supports popular programming languages such as Scala, Java, Python, R, etc. So broadly speaking, there's an integration layer in Spark. We have support for popular programming languages as well as SQL platforms. And then there's a simple unification layer that is packed with a high-level API for manipulating structured and semi-structured data, and that's our data plane API. And finally, we have a speed layer that is our Catalyst optimizer built in the constant execution framework, and that gives you very high performance for your distributed big data workloads. And basically, a combination of these factors allows you to build very robust pipelines on your streaming data with minimal amount of coding. And that brings us to what we call structured streaming. In specific, structured streaming is a high-level API that is built on top of the Spark SQL engine. So now you're able to express your streaming workloads entirely in a SQL paradigm or SQL framework. And it allows you to run your batch queries on top on top of your streaming data. So now you can take your SQL queries exactly how they are, and you can transport them to your streaming data and run them on your streaming data. There's a lot of community support in structured streaming, so it supports many sources and sinks that you saw on the slide previously. You can stream data from many cloud storage systems, you can stream data from message buses, Kafka, Kinesis, even databases. And then there's a lot of sinks where you can send data as well. And then there are a lot of streaming data related semantics that often even experienced programmers have to bake into their code, such as end-to-end exactly once guarantees, late data handling, and all of that is already baked into structured streaming and abstracted away from the end user. So as an end user, you can really focus on the business logic, and you don't have to worry about engineering a streaming solution. But when we talk about doing machine learning on streaming data, there are still some limitations when it comes to structured streaming. So number one is, since we have to write the models from scratch, or write a lot of these algorithms from scratch for streaming, a lot of the models in Spark and transformers and estimators are still not supported. It's not ideal for continuous learning, so if you're constantly updating your model and enriching your model, you have to bring the stream down and then update the model and then take the stream back up. So it's not really a very graceful solution for streaming data. And then, so the ideal solution in that case is to use microservices, and I'll show you that in the demo. Okay, so these are the Databricks notebooks. Basically, this is the Databricks environment, and like here you can see, we have a Spark cluster running. I have 2 clusters running. If I go to the cluster stack, I can see I have 2 clusters. And this is the Databricks notebook, similar to the Jupyter notebook, but it's really built from the ground up for using Spark underneath. And so essentially what I'm going to do in this section is I'm going to classify the user's activity. So I have streaming data that is coming in already, and then I have this address. So I have an EC2 instance that is running as a microservice for the classification portion. So in this case, I'm going to create a user-defined function. So people who use Spark probably already know this. The function is called store activity. And essentially it's going to take, I'm going to feed the schema of the data, and in this case it's going to be the axial data, the user, the model, and the device. And then I'm going to use the Python URL lib2 to send this data, this row of data, constantly streaming in, and get an output or get a prediction from the microservice. And that is going to be my response. And I'm going to return that response back to Spark. I'm going to register this as a Spark UDF so I can run this within the Spark framework. And then if I want a logic for retries, I can have that as well. I'm going to skip over this one now. Now, in order for me to actually start reading in the streaming data, so in this case I have data on my S3 bucket. That is constantly streaming in. It's right here. So first I need to have a schema defined. I can also ask Spark to infer the schema if I wanted to, but in this case I want to define the schema specifically. And it's very easy for you to go, as I talked about earlier, it's very easy for you to go from batch computation to streaming computation in Spark. If I want to write the same logic with the batch computation for reading this data. So my data is in JSON format. All I have to say is spark.read.format, JSON, provide the schema, and then load and give the S3 directory where my data is stored. If I need to now move from the batch framework to a streaming framework, instead of saying read spark.read.format, I can just say spark.readstream. dot format. And that's how Spark knows that it's going to be getting streaming data and not batch or static data. What the schema of the data looks like. I have a data frame, so very similar to Panda's data frames. Spark also has a data frame API. So this is what my data frame essentially looks like. If I do a display, now if it was a static data frame, it would not say stream initializing. It would just display the data immediately. But since we have a streaming data frame, it says, you can see it's a streaming job. Here we can actually see the number of input records, the number of records processed, the latency versus throughput. I've already run this process once, so that's why you're seeing the graph fall off. This is not processing any records anymore. And the difference between batch and streaming data is basically that the streaming data does not have an end of file in the end. So as the data comes in, it will constantly keep updating. Okay, so I want to now run some ETL, run some transformations. In this case, I want to clean up the timestamp and have the timestamp in a format that Spark can understand. So I'm going to run this quick function to do that. Very straightforward. And then I'm going to window. So if you remember, I talked about how when I was building the model, I created an n-minute interval moving windows. So in this case, again, structured streaming allows you to do that very, very quickly, very straightforward. All I have to say is window, and I have 10-minute windows that are updating every 5 minutes. So the amount of code that you write to do these streaming computations is cut down by a lot if you're using Spark Streaming. And then if you wanted to account for late data arrival, so in this case I can say that I'm expecting data to be late by 1 minute. So in that case, I can just say with watermark and Spark will hold on for a minute before it commits the data for further transactions. So now I have a data frame which has data aggregated on a 10-minute interval, and I'm going to register that as a table or a view. What that means is that once I register this as a view, it will allow me to run SQL queries on top of this data, on top of the streaming data. So I call this activity recognition, and now you can see within the Databricks notebook, if I just say %SQL, I can run SQL queries on top of this streaming data. So what I do is I say select window, that is the window that we just created, and then in window, the x-axis aggregate, the y-axis aggregate, the z-axis aggregate, the user model device, and then I feed it to the UDF that we had created earlier, if you remember. And that UDF is calling URL 2 in Python, that is going to a microservice and getting a response of the table of the activity from the classification algorithm that we have written. So I'm going to call this UDF, and the response from this UDF I call this response. And here you can see if I run this, I have the it's also doing quite a bit of a hop. It's going from the Databricks network where I'm running this process into an EC2 instance, which might be making this. Okay, let's look at this. So essentially, the response that I'm getting is the window we had sent to the microservice, and the response was the actual prediction and the probability. So in this case, the algorithm is saying the prediction of this row of data is that the user is going down the stairs, and the probability of that is 100%. And now I can actually see what the activity of how many users are sitting, like what is the what activities are different users engaging in, and I can aggregate that on a graph. within the notebook itself. And in case of streaming data, these graphs will keep updating in real time as well. And then I need to send this data back to another model, which is going to cluster the users together in real time. So in order to do that, I'm going to just write this data frame out to S3, which is going to call, and then we're going to have another process that is going to call the model, the k-means clustering model, to do the affinity sort. So that's exactly what I do here. In order to write the data, all I have to say is write stream, and in that way, Spark will continually write the streaming data out to S3 or any other sync of your choice. So I'm going to switch notebooks here. I'm going to go to my second notebook. So this is the part where I actually cluster users together. So once I have the data that has been written out to S3, I can create another data frame, and I can do some cross tabulation. So I can I have in this case a pivot table that I create where I pivot by the activity, and I have 7 users here, and I see what their activity chart looks like. Once I have this, I can just feed this to another UDF, and this is calling a separate microservice which has a different advertised address here. And that UDF is essentially going to take this cross-tabulated data and feed it to another model, and it's going to get a response of which users belong to which group. And I'm going to register this as another UDF, and now I can run this on my cluster storing view. So that is, I create another view with the cross-tabulated data, and I can now run the SQL query with this UDF cluster users, and essentially the output of that will be which group do these individual users belong to. Right now, we don't have that much data, so you're going to see them all bucketed in one group. But if you have enough data, and you start scaling out, you'll see people will start, these different users will start getting bucketed in different groups, so they're all based on their activity. Okay, so that's it for my talk and the demo. I talked about a lot of things. So we still have, we still have enough time to get any questions.
Any questions? So for scaling out those microservices, you said Databricks is going to be introducing ML flow, and that's like the same ML flow used like by things like Kubeflow and stuff like that, or this is different.
ML flow used by who?
Like Kubeflow, is it similar to that?
Yes, so it's slightly different. Kubeflow runs on Kubernetes natively. There are talks internally within Databricks, and we are talking with the Kubeflow labs to integrate ML flow. It does run on Docker images, so if you have a Docker infrastructure, you can use ML flow.
Right, so there any REST API inside of the Docker image you could deploy that way?
Correct.
Okay, thank you.
So what stack do you use for your microservices?
I'm using Docker.
Well, Docker as a container, but where are you building your microservice?
It's an EC2. It's on an EC2.
Correct, but what is your stack to actually build a microservice? Is that a Python type of microservice?
It's a Python. It's a Flask.
But it's Flask for me. And for this notebook, what is it?
These are Databricks notebooks.
What is it?
Databricks. So Databricks is a company that's based in Silicon Valley. It was founded by the creators of Apache Spark, who were basically PhD students writing their thesis at UC Berkeley, who basically came up with this concept of Apache Spark, and then they formed Databricks, a company that supports the Apache Spark project.
All right, thank you, Vedant.